All right, guys. So let's proceed with a new session on the trusses, and we are going to be talking about the member and node identification in the trusses. And we find out that there are some terminologies that we need to be familiar with. The node, for instance. So each one of these intersections of the two members or more than two members going to be called the node or the joint. And then we are going to be talking about the degrees of freedom. At every node, you have the number of degrees of freedom. For instance, this node is able to move in the horizontal direction and vertical direction, for instance. And these are the number of possible displacements for this node of the truss member. So at the node, these are the degrees of freedom, but for the structure itself, we have a total number of degrees of freedom. So we need to identify for the whole structure how many degrees of freedom that we will have. And the degree of freedom, meaning that the freedom to displace, basically, or to move. And there are some restrained degrees of freedom. Restrained degrees of freedom, that means at support, for instance. So degrees of freedom was restrained. So this is a pin support that's restraining the horizontal and vertical movement. If you have a roller support, is restraining one of the movements and allowing the other one. The nodal displacement is basically how much displacement this node will be. Let's say that you start with this and then it moves somewhere else, let's say, then there is a horizontal and vertical movement or displacement for that node. The nodal force that is identifying the force that's applied along the degree of freedom. So if you have the truss like that and you have a force here along the horizontal degree of freedom, do you have force or not? Here you don't have anything, so the force along the vertical degree of freedom is 0. The nodal displacements, basically we are trying to find out that the column that's indicating all the displacement is going to be in the right hand side, as you can see right here. That is the vector D. And the forces which is in the left hand side, the vector or the column that's indicating all the forces, is going to be right there to the left, and K is the relationship between the force and the displacement. So we just wanted to highlight this so we understand exactly what we're trying to find out. And we're going to be talking about what does that mean, K11 and K12 and K21 and all these methods or these entities. So to identify the displacement, for instance, I am going to specify each member. So first thing you need to do is we need to identify the elements or the members of the structures and identify the nodes. So for the members, for instance, you're going to have that square, as you can see here, 5 and 4. So this kind of square is identifying the members. So how many members do we have? 1, 2, 3, 4, 3, 4, and 5. So we have 5 members identified with that square. I need you to, when you submit your homework with the hand calculations, show me exactly what that is. And then the number which is enclosed in the circle at the nodes. So the nodes are going to be identified with circles. How many circles? We have 1, 2, 3, and 4. So you have 4 nodes and you have 5 members. And there's something called the near and far. So you see this arrow right there. So that's showing you that member 1 is between this node right here, 1 and 2. Member 3 is between 4 and 3. So it's going between 4 and 3. And this is very important when you assemble all these elements together to get the overall stiffness matrix of the structure. That will be very important that you follow that kind of procedure. So this is an example of the identification of the member in square, the nodes in circle, and the direction using there. So I just wanted to share that with you before we proceed so that we understand exactly how to solve the problem in a very easy way. Once you do that, you also need to establish the coordinate system. So what is the coordinate system? Let's say local coordinate system. So the local coordinate system for this member is basically x prime and y prime. This is the local coordinate system, but the big X and big Y, or this big arrows right there, this is a global stiffness matrix. So the global or the structure coordinate system will be used to specify the sense of each of the external forces and displacement components at the nodes, meaning that when you did the local coordinate system, you found displacements and forces. When you assemble them in the whole entire structure, you will be able to identify the total external displacements and external forces. So the local or member coordinate system is used for each member, as you can see right here. And that is going to show you and help you also to identify the internal force that's developed in this member. All right, that's something that we are going to be using. So this is very important and very easy and straightforward procedure. Then we're going to be talking about the kinematic indeterminacy and the degrees of freedom. And basically what we're saying that the unconstrained degrees of freedom of the truss is the unknown. That's nothing but the unknowns of any displacement method. All right. And then for each joint, there are 2 degrees of freedom, as we can see in the previous example. 2 degrees of freedom. One may be in the direction of the member and one perpendicular to direction. So at this node, for instance, you can see these are 2 degrees of freedom, for instance. For the overall structure, you can have it at about X and Y as you identified the global axis. Each degree freedom is specified using a code number. So this is again very important. This is you use a code number in order for you to identify. So if you can see here, you will be able to see in joint number 1 you have degree freedom 7 and degree freedom 8. In joint number 2 you have 3 and 4, 6 and 5, 1 and 2. So this is something that you need to pay attention to. That's basically what you need to know as far as the degrees of freedom. And the lowest number will always be used to identify the unknown displacements, meaning when we partition the matrix, you're going to see that the lowest number will identify the unknown displacements or the unconstrained degrees of freedom. However, the highest numbers will be used to identify the known displacement or the constraints degree of freedom. And that's in the partitioning that we are going to be using shortly. All right, so let's see just an example of what we're talking about. How many degrees of freedom you think in this truss, as you can see right here. Let's see how many nodes. 1, 2, 3, 4 nodes. At each node you have 2 degrees of freedom. So you have a total of 8 degrees of freedom. 1, 2, 3, 4, 5, 6, 7, and 8. Correct? So this is really amazing. This is exactly what we are looking for. But let me ask you something here. Why did we have that kind of numbering system? The whole idea is, look at where the supports are. Here is a support that is constraining and limiting and confining these degrees of freedom, correct? And you have a roller support here that's also restraining. So I'm going to circle the ones that are constraints. Those are the ones that they are constraints. So let's look at the others. This is free, correct? So if this is free, so I would say 1 in the horizontal direction, 2 in the vertical direction. Agree with me? What else? After you finish this, I have 3 and I have 4 degrees of freedom. And then here, should I move to the horizontal? No, we said this is constrained, so you only have that 5. So you have 5 degrees of freedom that are unconstrained. They are unknown. We don't know how much deformation we have. Again, you have 1 and 2 and 3 and 4 and 5. These are unconstrained degrees of freedom. That means it's unknown. We don't know how much deformation we have. However, 6, which is this, so let me try that with a different color. 6 and 7 and 8, they are constrained. So we know that the displacement here in this example, 0. So you have 0 here, as you can see. All right. So that is something that we need to figure out and understand and see how many unknowns. This is indeterminate to the fifth degree since we have 5 unknowns right here. However, for the example to the right, you have only 3 unknowns. The rest are all constraints, and we know that they are 0. So I hope that helps a little bit in order for us to understand what I mean by degrees of freedom. If that is the case, then we can proceed. Identification of the degrees of freedom, done. Identification of the B or the members, done. Identification of the nodes is done. I just wanted to highlight here what to expect from the out of your software. Basically, you have a truss, as you can see right here, and you have an applied force at the end, and we're trying to find out the forces that's developed in these members and the displacements at the joints, and figure out whether they are tension or compression. That is the whole idea behind what we're doing here in this example. I hope that helped, and we are going to be talking about the stiffness matrix, as we said earlier. Kij, as you can see right here, it's representing the amount of force that's required at I, direction of I, to cause a unit displacement at J, with the displacement at all other degrees of freedom equals 0. And what is that function of? It's the geometry of the system, the material properties, both modulus of elasticity and I, and the boundary conditions, meaning the support. 3 things again: the geometry of the system, the material properties, and the support conditions that you can see right here. Is that a function of external load? No, it's not. So this is something that be good to understand and just be familiar with. Once the truss elements are labeled and you are able to label the codes and everything, then you can establish the stiffness matrix that you will have. So this is something that is very nice to know. So once you have the truss labeled and the code numbers are specified, then the structural stiffness matrix can be determined as follows. Number 1, you can establish the member stiffness matrix K prime. Establish the member stiffness matrix K prime. And then move on to transform the element of the member stiffness matrix from the local to global coordinates, assemble them, and find out the total stiffness matrix. We will touch on that in the coming lecture. Thank you so much, and we will meet shortly.